Good morning, everyone. I will just make a brief intro to my tutorial this afternoon about analyzing space-time satellite data with GRASS GIS for environmental monitoring. We will work with the monthly LST MODIS data, and we will show like the different functionalities of the temporal framework in GRASS GIS. So most of you already know like a lot of basic concepts in GRASS GIS, so this should be easier for you because the basis is already there. Then I'll tell you a little bit about me. Okay, also maybe you already heard it, but I'm a biologist, so like Madeleine, don't ask me about statistics or anything like that. And then I did a master in the Argentinian Space Agency on remote sensing applications, and that's why I kind of shifted a bit. And I actually do remote sensing and GIS applications for disease ecology, which was my original topic. I work as a researcher in the Argentinian Space Agency, and I'm also part of the GRASS development team, and I'm a Geo Charter member. I used to teach GRASS courses, like also in Argentina, luckily now. Yeah, but there are some videos around. There you have like all the contact information, my website, and everything. You can check what I do if you are interested. So, GRASS GIS has become like the first FOSS GIS that has incorporated these capabilities to manage, analyze, process, and visualize spatio-temporal data. But not only that, but also the relationship among time series, and that is something quite novel. So we call this temporal grass, we call it TGRASS, so for short. This TGRASS is fully based on metadata, and it does not duplicate any data set. So most of you already know the concept of GRASS data and how it is organized. So it does not duplicate any of that, but it's just based on metadata. So what we add, this approach is called Snapshots. So what we do is basically add a timestamp to the maps that we already have in our GRASS data, in our folder, okay? And then a collection of timestamp maps of these snapshots is then called a space-time dataset. So this is like, or when it was introduced, it was like a new type of data in GRASS, but it's just collections of either raster or raster 3D or vector maps. And the maps within these space-time data sets can have different spatial extents and different temporal extents as well. So, as I said before, then we have this space-time raster dataset, or STRUDS, and so on, with 3D raster and with vector data, with vector maps. That becomes a little bit difficult to pronounce. And since last Saturday, we also have support for image collections. You can see there in the link, that's the pull request that was merged, but that's only in the development version. So far, we're not going to work with that. So some other TGRASS notions that are important then for the tutorial. The time can be defined as intervals, so with a start and end time, or as instances or point in time, and we only use then start time. So like an image, a satellite image, for example, we would use this type, instance time. And then also time can be absolute, like defined as in Gregorian calendar. the minimum resolution would be 1 second. Okay, we can have time series per second. That would be like the minimum temporal resolution. Or we could define time as relative, and just then each map represents whatever, like 10 days, 1 month, 1 year. That kind of time is mostly used probably in simulations, for example, when you don't care about the actual date, but just how much time it represents. Another concept is this temporal granularity, which is the greatest common divisor of all the temporal extents of maps within a time series. So I always put the example of MODIS 8-day products here, because you would say, okay, which is the granularity of a time series of MODIS 8-day products? 8 days. Well, no, because the last image per year, in each year, has like 4 days or 5 days, okay? Because then every 1st of January, it restarts. And then the greatest common divisor of 8, 5, and 4 will be 1. Okay, so a granularity of that time series will be 1 day. And that is then important for different temporal operations that we have to do. Another very important concept that allows us to relate time series of, let's say, different variables, for example, LST and NDVI, and try to do operations among them, is this topology. And it refers to the temporal relationships between time intervals in a space-time dataset, or between space-time datasets. And so these are the relationships that are supported, a subset of the relationships that are supported, and some of them just change according to which series you put first, okay? Another concept that has to do a lot with temporal topology is the temporal sampling, and that's how you, when you actually are relating two time series and you want to either sample one with the other, for example, you have a time series of vector data, and with that one you want to sample raster time series. So you see which raster will you sample according to the intervals of each time series. Okay, so in this table then you have how you sample each one, okay? And then the same as with all the modules in GRASS, they are organized with according to their functionality or according to the input data that they take. And so all the modules starting only with T will be related to general modules to handle time series. And then if they are TGRASS and something else, those are specific for raster time series, and so on with raster 3D and vector. So this is a very beautiful plot. No, what I wanted to represent there is like the general framework and how the temporal framework is immersed or embedded into the GRASS data structure that we saw yesterday in the work, in the tutorials with Marcos. And so up there we have our GRASS database. That would be our GRASS data folder, okay, with our rasters, 3D rasters and vector maps. And with those maps there, we can create time series just by assigning timestamps to them, okay? So it's just adding some metadata. And what we do actually when we use this tcreate module that would be like the first step in the workflow is just create a table that will contain like all the names of these maps that we will assign timestamps. Not only the names, but also it will include the spatial extent, the temporal extent, and the minimum and maximum value of the map, okay? So it's indeed, in the end, a time series in GRASS is just a table with all the maps and the metadata. So we're not duplicating, we're not We don't need to import the maps again and create a cube of maps or a stacks of maps and then like increasing the size of files, but it's just registering them in a table, which is the second step, assign timestamps to maps. And for that, we use a command called tRegister. And like that, we get these space-time data sets for different types of data. And that is what we call the temporal database. And then after that, we can start our processings. We can use specific T modules, but we can also use some other modules in GRASS Core or add-ons that are very useful for time series as well. So for visualization, for example, we have those models there, starting with GUI. So for timeline, we can do GUI tplot, like clicking in everywhere, like in a map. And if that map belongs to a time series, we then can see how the time series would look like in that pixel. Okay, so we get plots like that. Or we can do animations as well. Then we can do different listings, selections, extractions of maps. Yes, always using the date or the variables that are stored in this table. Yes. So we can select, for example, from one day to the other where the minimum is higher than something, things like that. Then we have some pre-processing tools like adding a color table or filling gaps, for example, like with just linear interpolation. Or we can use other modules to do gap filling. For example, our hands there, here, our hands, or local weighted regression as well. So for example, for NDVI, we could use our hands because it's like a periodic phenomenon, okay? And Hans is harmonic analysis of time series, so it's based in Fourier series. And then the core of TGRASS is the algebra part, and we have like also different modules there. We have different aggregations that we can perform, like these reducers that we were seeing in GDAL cubes. So one of them is TGRASS series. That would be like a temporal reducer in GDAL cubes. But then we also have this TGRASS aggregate that allows us to aggregate a time series according to a granularity that we can specify. So we can aggregate, I don't know, if we have monthly data and we want 3-month data, we just put 3 months. So, and that's it. And then your time series gets aggregated by every 3 months. And then the algebra. This is like super powerful module, but also quite complex. The syntax is quite complex, but it allows to do a lot of operations, like with spatial topology, with temporal topology, with different temporal operators. You can shift the time, you can snap the time, you can buffer in time. You also have like temporal neighborhoods, spatial and temporal neighborhoods, so you could create like space-time filters in your time series. There's a lot of things. We will use just some very basic examples. There's also algebra for vectors, and that would allow as well to do like buffering in space-time for vectors and such. Never used it. I never used it, so I actually don't know. And then we also have like accumulations, for example, to estimate growing degree days. For those of you more into, I don't know, maybe agronomy or some ecology, you know that plants and insects depend on temperature for either blooming or developing and such. And so you can estimate the growing degree days, and then according to the biological cycle of your other insect or plant or whatever, you can see where the cycles are met, when do they start or could start, and spatially where. So it's also really, really nice to see. Well, for me, it's really nice to see. And then afterwards, you can also import and export your time series and, for example, take it into R if you want. Yeah, and then there are like some other modules, for example, to extract information from the time series, like with just one vector, you get, you sample, you extract information from all the raster time series, or zonal statistics from a time series and things like that. So what we will do is first a bit a short intro about the data that we will use. Then we will go through modules, through these modules I showed in the diagram, explain them, and directly go to hands-on to create a time series, register maps in the time series, use algebra to convert MODIS LST that comes in Kelvin to Celsius degrees. And then we will do some temporal operations like extract the date of the maximum LST of the year and the date of the minimum and things like that. Temporal aggregations, estimate climatologies and anomalies. And then we will do some exercise to estimate to calculate the surface urban heat island. You know that this is a phenomenon pretty important in urban areas that affects health and biodiversity and water management and different things in cities. And we will use this example as an excuse to extract zonal statistics, both from urban areas and their surroundings, and then take this data to R and do some plotting. So I will show you in the very end of the tutorial how to connect GRASS with R. Okay? Like without leaving GRASS, just open R, bring our data, and do some plottings. Okay? Okay, we will use this already prepared location. It's actually the North Carolina location that comes with GRASS, but we added some things there. We added some map sets. One is for LST that we will use today, and one is for NDVI that we will use on Friday, which is the same lesson but with a different time series. So it was not that boring to repeat again the same. Sorry for that. So basically, you can start, if you want to take this tutorial, just start with downloading the data and the code. They are in the link. The North Carolina state is this one. There. So we will use data from this state. And as I said before, just a little bit more of detail about the data we will use. It comes from the MODIS 11B3 collection 6 product. It's a tiled monthly composite. And that's the number of the tile corresponding to North Carolina state. It has a spatial resolution of 5,600 meters that corresponds to most climatic global models. And the selected time period is from 2015 until 2017. So basically that's it. And here I leave you some references of the developer of these modules and of this temporal framework. Is Søren Gebert, and Edser was the supervisor, right? And some other very useful links for temporal. If you don't want to take the tutorial, you can just take some tour through these links. There's a temporal data wiki, and then a wiki connecting GRASS with R for time series as well, and some other workshops and courses around the world, going from 0 in GRASS to advanced. There are different flavors, some using more Python, some using more R, and so. And so please join and enjoy. And let's talk GRASS.